Welcome, ladies and gentlemen, to this video lecture. Okay, so now we will move on to a new section on what is called Taylor polynomials. Okay, so let me motivate why Taylor polynomials are important. So I'm just going to open up Wolfram Alpha here, and I'm just going to use it as a calculator. So and I'm going to use it to calculate the sine of 1. And the sine of 1 is 0.841470984, etc. And the sine of 1, that is actually irrational, so this number is just an approximation to the actual value of the sine of 1. How does the computer know what the sine of 1 actually is? So we can get a closer and closer, or we can get quite a close approximation for the sine of 1, but since it is irrational, the approximation, the number of digits will never stop. How does the computer actually know what the sine of 1 is? Okay, so it appears to be some kind of magic. Somehow, magically, the computer is able to work out what the digits of the sine of 1 is, even though it is an irrational number. So the number of digits in the approximation for or the decimal representation for the sine of 1 continues infinitely. Somehow we are able to compute what these numbers are. How does that work? So one way of doing it, there are many ways of doing it, but one way of doing it is to use Taylor polynomials. So now what I'm going to do is I'm going to demonstrate to you just by graphing some Taylor polynomials. So we are interested in sine. So there we've got a nice sine graph, nothing special. So now let us take a look at how the following polynomials relate to the sine function. So I'm just going to plot the polynomial x, or plot the graph of the polynomial x. And we see here this x matches quite closely here, the sine graph. Now I'm going to add another term. I'm going to say minus x cubed over 3 factorial. And we see, we get an even better approximation. And now I'm going to say plus x to the 5 all over 5 factorial. And now we get an even better approximation. So up to just, let's say up to about 2, we have a fairly decent approximation for sine. And then later on, the polynomial tends to blow up. So over here, we don't have a very good approximation for sine, but close to 0, we have quite a good approximation for sine. Let's add another term. Let's add minus x to the 7 over 7 factorial. And we see now here, we used to have a good approximation up to 2, and now we have a good approximation that looks to be about at 3. And then after 3, the approximation tends to diverge from the actual function. Let's add another term, plus x to the 9 over 9 factorial. Let's see. Now we've got a good approximation up to from about -4 to 4. Okay. So somehow, if we could choose polynomials somehow, well, we don't know how to find these polynomials, but if we can find these polynomials, then we can, if we want an approximation for the sign of 1, then we just instead of plugging it into the sine function, well, sine function is geometrically defined, so it's very difficult to find a value for the sign of 1. However, if we have this approximation, this red function, which is just a polynomial, we can plug 1 in for x there, and then obtain an approximation for the sign of 1. And let's see if that is actually the case. So what I'm going to do is I'm just going to copy this part, and let's see what we get. So let's see if we can do this. So instead of x, I'm just going to put in 1 for every value of x here and see what we get. So what do we expect to get? We previously saw that a good approximation for sine of 1 is 841,470. Let's see if we get that or something similar. So let's plug that in. 841,471. Okay, so somehow this polynomial is able to give an approximation for the sign of 1, which is quite magical. It's really quite magical. So here I have made a little slider so we can you see there is some pattern to this polynomial here. It goes x minus x cubed plus x to the 5 over minus x to the 7, so all the odd terms. So here I've made a slider that manipulates the number of terms that we have in our polynomial, and we see here the more terms and the higher order the terms we add to our polynomial, the closer our approximation gets. So if we have up to 50 terms, this polynomial in blue gives quite a fairly good approximation for sine up to 35. Okay, and the more terms we have, the closer our approximation gets. So another thing that we want is, well, we are only getting approximations for the value of, for example, the sign of 1. How close is this approximation? Because we want to know how big is the error that we're making. So over here, even though we've got 50 terms in our polynomial, over here we're making very large errors. So over here it's saying that looks to be about the sign of 37. It's going to say the sign of 37 is minus 20, even though we know that sine always takes values between -1 and -1 and +1. So over here at 37, even though we've got 50 terms in our polynomial, it is making a very large error, and we want to be able to quantify the errors that we make in making this approximation. So there are two questions that we need to answer. How do we find these polynomials? That's number one. Because if we have these polynomials, then we can make approximations to functions, and we can work out the value of those functions, or approximations to the value of those functions. And since we are only making approximations, there is some error involved. How big is the error that we are making? So those are the two questions that we will answer in this section. And my personal opinion is that this section is, or Taylor polynomials are quite magical. It's nearly unbelievable that they work, and we will see some of that in this section. I will see you in the next one.